Hello everyone, welcome to lecture 27 of AREC 333. Today we will continue with the linear programming topic. This is the last lecture before reading week, and I'm actually hoping that I can finish this linear programming topic by today. So after reading week, we will start with a new topic, which is risk and production. But let's see if we can finish. If not, then maybe we will leave a little bit to the week after reading week. So today we will continue with the farm management example that we have been working on. I do want to let you guys know that although this farm management example is a little bit more complicated, in the exam or in your assignment, I will not ask you to set up a complicated example like this. The level of difficulty for final exam will be similar to the level that you are seeing for your assignment 4 or assignment 5. So your assignment is a good indication of the level of difficulty for your final exam. I do want to have you guys exposed to a little bit more complicated linear programming example and show you how powerful it is. So today we will continue with interpreting the sensitivity report. We were almost done with this in last lecture. There's only one small step left in this section, which is the reduced cost. If you look at the sensitivity report you generated from this example. So I will spend a little bit of time explaining of the information included for that column. And then after that, I will also show you how you can actually derive the output supply function and input demand function from this linear programming problem. So I hope those two concepts are not totally new to you, because we in the production function analysis or the marginal analysis sections, we did derive both the input demand function and the output supply function. And we actually, for the input demand function, we also derived the conditional input demand and the unconditional input demand function. But here in this linear programming topic, the input demand function and the output supply function are still the same, but the steps of deriving them are different. And I hope you can actually enjoy this. So the suggest ratings are still the same. And here I still recommend that you read this Kim et al. 2018 book. They have very detailed explanation of the sensitivity report. So if you feel that I'm not explaining stuff clearly, you can maybe read their section, so it will help you understand this topic better. We spent quite some time interpreting the sensitivity report in last lecture, and there's actually one more thing left that we didn't cover in last lecture, which is the reduced cost. So this is from the part 1 of your sensitivity report. So what this reduced cost I highlighted here, if you pay attention here, is that for those variables where the optimal solution is 0, the reduced cost is non-zero. And for those variables where the optimal solution is greater than 0, then the reduced cost is 0. And there's a reason why. But first, the reduced cost is the amount by which the objective function value will change if the corresponding variable change from 0 to 1. So this is for those variables that the optimal solution is 0. So basically, take cell beans, for example. If this value change from 0 to 1, then what will happen to the objective function value is that the profit will decrease by 1.4945. So that is actually kind of linked to the concept of shadow price. So shadow price is also telling you what's gonna change to the objective function value if you relax the right-hand side value of a constraint. So let me explain it a little bit in more detail here. So first is that reduced costs for those variable where the optimal solution is 0 is actually the shadow price for the non-negativity constraints. I haven't actually explained what is a non-negativity constraint. So this is basically the non-negativity constraint is basically saying that, for example, if our decision variable is x1 and x2, so take the tomato example, and those are the number of acres to grow potato and tomato, which means that those values should be greater or equal to 0, and it's non-negative, which is why it's called non-negativity constraints. We didn't, when we're writing the linear programming problem, we didn't explicitly write this down. It's because when we're solving this linear programming problem in Excel solver, there was a box where if you check the variables are non-negative, it's already imposing this non-negative constraints. So I will show you in a little bit in Excel where is that box, and I believe you have already done this. So this non-negative constraints here, for example, for cell bins, which is mean that cell bin that decision variable should be greater or equal to 0. And if we relax the right-hand side value from 0 to 1, change the right-hand value from 0 to 1, then the shadow price is actually the change in the objective function value. So here, if we change this constraint that we have already implicitly imposed to cell being greater or equal to 1, then the objective function value will increase by this negative number. Or you can say in another way is that the objective function value will decrease by 1.4945. However, for the variables, for example, here cell corn, the optimal solution is already greater than 0. Then if you change the non-negative constraint from greater or equal to 0 to greater or equal to 1, then there will not be any change to the objective function value. Why is that? It's because if you look at the optimal solution, this solution is already greater than 1, then adding this constraint is not changing anything. So that's why its reduced cost is 0. Let me actually show you this in the Excel template that we have been using. What is the reduced cost there, and what's the linkage with the shadow price? So let me show you in Excel where you can find the reduced cost and where you can find the box for the non-negative constraints. First is this is the template that we have been using. Let's try to solve it. You click Data, Solver, and this box is actually the box you check to make the unconstrained variables non-negative. So this box, if you check it, it actually means that all of the decision variables here, that their value will be non-negative, or if you put it another way, it's greater or equal to 0. So it's similar if you don't check that box, and you, in this constraint section, you actually add another 12 constraint here. In this row, you're saying that cell corn is greater or equal to 0, raised corn is greater or equal to 0 in another row. So you actually, because solver allow you to make that check that box, you actually can save some space here. You don't need to explicitly write down the constraint, the non-negative constraint. It's already kind of embedded in the solver. So let's solve this problem again. So make sure you check this. This is where your variables are non-negative. And if you solve it, you generate the sensitivity reports. And here is the sensitivity report generated. You will notice this is the column of the reduced costs. And if you pay attention to this row, this is a cell bin. This is the example that I used in the slide. So the reduced cost for this cell bin is negative 1.4945. And this reduced cost for those variables is actually gonna be the shadow price for those non-negative constraints. If here in this constraint section in the setup you included all of the non-negative constraints and then you generate a report, then here this section all of those shadow price for the non-negative constraint will show up here. Let me actually add one constraint to tell you the difference. So let's add the constraint that cell bins should be greater or equal to 0. So the easiest way you can add a constraint using this template is actually try to copy any constraint that is here and then just paste it. This is the easiest way of trying to make your own constraint, because there was a formula here. If you're not copying the constraints that's already in the template, then you have to come up with this formula here yourself. So let's use what is here, make changes. So let's first change the name to cell bins, and the unit should be bushels. So the constraint should be cell bins is greater or equal to 0. So here it should be greater or equal to 0. So this constraint is explicitly saying that cell bin is greater or equal to 0. So this is one non-negative constraint. You can add the other non-negative constraints for each of those decision variables, but I just want to showcase one constraint. So now we click solver, and we actually need to this time add one more constraint here. So add the constraint of this value need to be greater or equal to this value here, which is 0. So we add one more constraint here. This is a non-negative constraint for cell bins, and let's solve the problem again. And let's also generate the sensitivity report so that you will know what's the difference. So here, once we explicitly saying that the cell bins need to be greater or equal to 0, we'll notice that here there's one more constraint, which is a cell bins total here, and there is a shadow price here. So then if you go back to the reduced cost here, there's actually for the cell bins it's 0 there, because now since you included the constraint, it's the shadow price of that constraint, of that non-negative constraint. If you go back to the original sensitivity report here, where you didn't explicitly write down the non-negative constraint, you will notice here there's no cell bins constraint, so you cannot find the shadow price there. However, the reduced cost here is really the shadow price there. So you can compare the values here. If you have the time, you can actually add all of the non-negative constraints here and check your sensitivity report. There will also be all of the shadow prices there, and you will find that the shadow prices are actually the same as the reduced cost here. So it's basically the same thing. So this reduced cost column here is just the shadow price for the non-negative constraints. It just saves your time of writing this constraint, so you don't actually need to explicitly write this. You just need to in here check this box, then it's already having all the non-negative all of the non-negative constraints. So that's what the reduced costs are. There's one more thing I want to show you, but let me get rid of those two sensitivity reports first. And we mentioned that the reduced cost is actually what's gonna happen to the objective function value if you relax this non-negative constraint from 0, the right-hand side value of this from 0 to 1. So let's actually change this to 1 and let's check what happened to the objective function value. And I do want to show you that the change to the objective function value is exactly what was the shadow price for this non-negative constraint, or it was also the reduced cost if you don't have this non-negative constraint explicitly. So let's actually change this to 1. So we are relaxing the right-hand side value of this constraint from 0 to 1. And then let's solve this problem again. And we don't need to make changes here because we only changed the coefficients, the parameter values. So here, let's actually generate both the sensitivity report and the answer report. So you can very quickly check that this value was 0 before, and now because we are imposing the constraint that cell bins need to be greater or equal to 1, so this solution changed. Let's actually take a look at the answer report. So here you can see this variable, the optimal solution changed from 0 to 1. And what I want to show you is a change in the objective function value. So it's this cell minus that cell. Let me format these cells a little bit differently so that you will see the value here. So after we impose the constraint that cell bins need to be greater or equal to 1, so again, this column is where the constraint is cell bins need to be greater or equal to 0. And this column is where the cell bins need to be greater or equal to 1. So you can see the change in the objective function value is minus 1.4945. And that was exactly the shadow price for that non-negative constraint. And if we go back here, we can actually get rid of these constraints, and let me get rid of all those and solve this problem again, and you will show where it was. So let me get rid of this constraint. So solve it and generate the sensitivity report. So this will be exactly the same before we made any changes to the template, and this was the original sensitivity report where we didn't add any explicit non-negative constraint here. And this reduced cost, as I mentioned, is the shadow price for the non-negative constraint. And you can see for cell bins, this is minus 1.49. That tells you if you change the non-negative constraint of cell bin greater or equal to 0 to cell bins greater or equal to 1, then what's the change on your objective function value. So this is exactly what's happening here in the answer report. Changing is negative 1.4945. So that's the meaning of the reduced cost. Reduced cost, if you pay attention to the sensitivity report close enough, you will notice that it is also linked to another value in the sensitivity report. So pay attention here that the reduced cost is minus 1.4945. And if you take a look at the allowable increase, it's actually the negative of the reduced cost. So this is also true for the buy corn. So you can also say here it is the allowable increase. So this is true for those variables where the optimal solution is 0. So it is telling you the amount by which the objective coefficient. So for example, here this 2.5, it have to increase, and before it is possible for this variable to assume a positive value. So for example, here, if the increase in the soybean selling price is $1, so that it becomes to $3.5, then this value will still be 0 because this increase is smaller than the 1.495. However, if you increase this objective function value by, let's say, 2, so this 2 is greater than the 1.4945, so then the new price is 4.5, then this value will be positive. It will not be 0 anymore. So that's the reduced cost linkages with the allowable increase for those values. With that, we actually have a question here. So currently, there's no soybeans being sold. This is actually sold. And because there's no soybeans being sold, so there's also no soybeans being produced. This is actually a value of 0. I will come back to this in a little bit. But here, there's no soybeans being sold and produced. What would be the selling price that soybean would be produced? So would be produced means that it's greater than 0. So it's a 3, 5, 10, or maybe never. So let's look at this. I just explained to you that if it increased by $1, by $2, then what's gonna happen? Let's look at this $3. So $3 compared to this 2.5, it's increased by 0.5. And since this increase is smaller than this 1.4945, that means if it's $3, then the soybeans is still gonna be 0. And what about $5? So $5, if you compare to this 2.5, it's increased by 2.5. And this is greater than the 1.4945, and this value will change. It's not 0 anymore. So you actually should play with the Excel templates and try to change the objective function, the objective coefficient for this soybeans. So try to change this number and change it to 3, 5, and 10 and see if what I have just explained is correct. So the answer here is this one, no. This one, so no soybeans will be produced. This $5, yes, and $10 is also yes. So that's the linkages between reduced cost and allowable increase and the objective coefficient. So I do want to explain here a little bit more. This is specific to Excel, the extreme values in the reports. I don't know if you guys pay attention here when you see these weird numbers there. What are those numbers? So what I want to explain here is that those numbers are actually, this number is actually 0. That number is actually infinity. So this is Excel's way of showing infinity, and let me actually explain to you why this is 0 and this is infinity. So Excel, if it says e plus something, that means it is this number. So let's take another number here. This number actually means it's 2.72 times 10 to the power of 14. So that's the value for that number. And if you imagine 10 to the power of 14, what is that number? It's really a big number. And that is just Excel's way of saying it's a big number. So if you say this number, that means it's 1 times 10 to the e to the power of 30. This is, I believe, the largest number that Excel can handle. This, if you ever say this number, this is infinity. So this is infinity, infinity, infinity. So if the allowable increase is infinity, that means you can increase this objective coefficient any number you want, and that wouldn't change your solution here. So that's the infinity. But you may wonder, this value, it doesn't seem like infinity. Why do you still say that it's infinity? It's because the way that Excel or the solver try to give you the solutions, the linear programming problem solutions, it usually have some tolerance level. And those tolerance value, you can actually change it, but most of the time it's very small. And because of the set in that tolerance, that Excel will stop. Sometimes claim it found a solution once it reached the tolerance level you set, and because of that very small tolerance you set, then here you actually get this number. And really, this is a really big number, and you should interpret it also as infinity. And let's get back to this number here. So this number, this is actually a number 3.55271 times 10 to the minus 15. So because here it's minus sign, it's not plus sign. So 10 to the minus of 15, if you draw the graph of the exponential function, it is really coming to this level. It's really close to 0 when you're having this power. So 10 to the minus 15 is 0. That's why if you this number times 0, then it's 0. So even if here the solution is reporting this value, but you should really interpreting it as a value of 0. So you may say, oh, those are zeros, but this one is not. That's not correct. It's just Excel way of saying 0. So this value is really 0. And here are some more examples. These are from the sensitivity report. So really, this is 0. This is 0, 0. This is 0, and this is positive infinity. Those two infinity, infinity, and this number is 0. And that's pretty much for the sensitivity analysis. A quick summary here is that sensitivity analysis, we covered both what if you change the objective function value and what if you change the right-hand side values. Then you can do some sensitivity analysis based on the sensitivity report that was generated by solver. We didn't cover a third type of parameters, which are the technical coefficients. So that one we didn't cover in this course. And we did cover if there's change in the objective function coefficient, then you can tell
based on the sensitivity report, what's going to happen to the optimal solution. However, just based on the sensitivity report, you cannot directly tell what's the change to the objective function value. If the optimal solution does not change, then you can probably tell the change to the objective function value. However, if the optimal solution change, then you have to resolve the problem with the new objective function coefficient. And when does the optimal solution change? So based on your sensitivity report, you first need to find the range of optimality. If the new objective function coefficient is out of that range, then your optimal solution change. And if your new objective function coefficient is within the range of optimality, then your optimal solution does not change, and you know what will be the new objective function value. On the other hand, if the right-hand side value changes, and if this is within, again, the range of optimality, then the optimal objective function value change linearly. Why is this? Is because you have the shadow price. So if it's within the range, then you know for 1 unit of the change in the right-hand side value, we used the length as an example, change from 250 to 251. So for each 1 unit of the change, then the change on the objective function value is the shadow price. So if you change this length by L unit and make sure that your new right-hand side value is still within the range, then the change on your objective function value is L times your shadow price. So that's why we say it's changing linearly, because this is a linear relationship. However, based on the sensitivity report for the right-hand side values or for the constraints, you cannot tell how the optimal solutions change. And we did show this in the lectures. So be careful about whether the question is asking what will happen to the optimal solution or what will happen to the objective function value. So then, depending on the question is asking, ask you to do sensitivity analysis about objective function coefficient or right-hand side values. So you need to be careful, very careful here. First is you need to differentiate between optimal solution and optimal objective function value. And then you also need to be careful about if it's a change in the right-hand side value or if it's change on the objective function coefficient.
That's pretty much the sensitivity analysis that I want to share with you for this course. And I do want to move on to a different topic, which is still linear programming, but we are actually able to generate the output supply and the input demand functions. So the way that you generate those two will be similar, but let's first work on the output supply. So what is the output supply function? And we actually did this before. So for the production function analysis, we mentioned that output supply function is part of the MC curve. So it is the quantity that the producer is willing to supply and the price of the output. And of course, you're holding everything else constant, ceteris paribus. So here, let's use corn as a example here. So this is from your sensitivity report. And if you read this cell corn row there, and you can actually find currently the objective coefficient is 1.3. So that is the price for selling corn. And there's allowable increase and allowable decrease. So the information you can get from here is that the range of optimality you can actually calculate based on the coefficient, the allowable increase and the allowable decrease. So this term here is 1.3 minus the allowable decrease, and this number is 1.3 plus the allowable increase. So that's how you get the range of optimality. And if it's within that range, then the corn that the producer is willing to sell is actually this number. So this is your optimal solution. So we can write it here. That's the corn price. If the corn price is within that range, then this is the amount that the producer is willing to sell. And we can do a little bit more is that this time we want to know what if the price is outside of that range, then what is the optimal solution? What is the quantity that the producer is willing to sell? So what we want to do is that since we know within this range, the optimal solution doesn't change. So we should try a price that is outside of this range. But let's start first show what if the price is a little bit below this lower bound here. So I chose 0.93. And then if I chose that, I go back to the Excel template. I change the objective function coefficient there from 1.3 to this new number. And then I solve my problem again. I generate a sensitivity report. And in the sensitivity report now, it also has the allowable increase and allowable decrease. So I'm able to get a new range of optimality and a new quantity that the producer is willing to sell, which is this number here. And if you observe these two ranges, you can see that this number and that number, there's actually a gap in between. So what you want to do is now I will choose a number that is in between those two range. So this one and that one. So I chose a number 0.935. You might choose another different number, maybe for example, 0.940. And then you solve your problem again. So this time, when I solve this problem again, like go back to the template, change the objective function coefficient, and then generate the sensitivity report. So this is a report for the coefficient, which is equal to 0.935. And I again get the allowable increase and allowable decrease. I calculate the range of optimality. And this time, this is a new range of optimality. And I compare this range with the other two ranges that I previously have. And it seems like there's no gap anymore. And then I want to do the analysis a little bit further, which is reduce the price even to an even lower number. So for example, this time, let's say the price is 0.9 and get new range of optimality. And this time, if you pay attention here, that we actually have the optimal solution is 0. We have this allowable increase, allowable decrease, which is infinity. So we calculate this new range, and we get the range which is negative infinity to this number. So this time it seems there's no gap between that lower bound and this upper bound. So we are okay here. And we find that within this range, the quantity to sell is actually 0. And because the lower bound for here, for this new range is negative infinity, and we cannot reduce the price any more than a negative infinity. So we stopped going for a lower price, and now we change our direction and go for a higher price. So now let's try a new price. I tried 1.5. Remember, it was 1.3 before. So now I tried it and I get a new range of optimality, and this is the new range of optimality. And remember, this is the positive infinity, which is this number here. So it seems like there's no gap between this number and that number, and I do find out the new quantity that the producer is willing to sell. And I also find that I also reached the upper bound, which is positive infinity, so I cannot change the price anymore. I reach both the lower bound and the upper bound. So based on the information that I get, I put them all in this table here, and I get a relationship between the optimal corn output, or the quantity that the producer is willing to sell, and the corn price, and that is the output supply function. If I put them together on a graph, and I have on the horizontal axis, which is a corn output, and on the vertical axis, which is a price. This is usually the setup we use in economics, is that we always have the price on the vertical axis and the quantities on the horizontal axis. And we actually is able to plot this output supply function, and this might be a little bit different from the output supply function that you usually see. Usually it will be a smooth curve like that, a supply function. And here, this is actually step functions here, like you take a value for a range and then change to a different value for another range. However, it is consistent with the output supply function that this is the upward sloping function, and which is true for the supply functions, is that if the price is higher, then the producer is willing to supply more. So that's how you get this output supply function. And similarly, once you have the output supply function, you can do all those analysis where if you have demand curve and you have the supply curves, then you can do all the analysis that you like. So similarly, we can also generate a input demand function based on the sensitivity report. So let me take another example here. However, this time we're not focusing on the objective function coefficient. This time we're focusing on the right-hand side value. This is because usually this is constrained on the input. So for example, labor or the capital, those are all inputs used to produce products, and input demand function is a relationship between the input prices and also the quantity demand for those inputs. So we can say if the right-hand side value change, or if they, then how will the shadow price change? So it's a relationship between shadow price and input use level. So this is a little bit different from the input demand function that you have seen before. You have seen in the production function analysis, it's a relationship between input price, a given input price. However, here we calculated the shadow price. So shadow price usually sometimes, or most of the time, it's not observable. It is some price. It's a price that the producer is willing to pay, and this is actually what we get from the analysis. We through our linear programming problem, solve it using sensitivity analysis. This is actually what we were able to infer that should be the price that the producer is willing to pay. So again, let's use an example. Let's choose labor this time. And if you go back to your sensitivity analysis report, you can find for this row here, we have this right-hand side value, which is 1500 there. And it also have a allowable increase and allowable decrease. So the allowable increase and allowable decrease is the amount you can change your right-hand side value without change your shadow price. So we can put this information here. The shadow price is 2.65, and that is the price that the producer is willing to pay for labor. It's not the actual price, but it's the price that's internal to the producer. And we can find this range of feasibility. So 2125 is 1500 plus this allowable increase, and the other side is 0 because 1500 minus 1500 is 0. So we already reached the lower bound here, 0. It's because we cannot, or the producer cannot produce negative number of labor. So here it is already reached the lower bound. So what we should do is we should increase the right-hand side value and then see what's a new shadow price. So let's change it to a number that is slightly above this upper bound here. And I change it to this number, and we go back to the Excel template. We change the right-hand side value for the labor constraint to this number. And then we resolve the linear programming problem. We generate the sensitivity report. And this time, we find out that the shadow price is 1.45. And under this price, we also know the range of the right-hand side value that the shadow price remains the same. So we generated a new range, and it seems we hasn't reached the upper bound, so we should increase the right-hand side value a little bit more. And this time, let's change it to a number that's slightly above here. And sorry, we should be here. So it's 2826. And then once we change it, the right-hand side value to this number, we find the shadow price is 0. So the producer is not willing to pay for any labor that is actually above that amount. So we get the new shadow price, and we also get the new range of right-hand side values for that shadow price. And we do find that we reached the upper bound here, which is positive infinity. So within this range, the producer is willing to pay 0 shadow price, which also means that the producer is not willing to pay for any labor amount that is within that range. So here we again was able to gather the information for the relationship between labor, the range of the right-hand side values, and the shadow price of labor. And we can also put it to a graph. So here, you can also see here, the quantities are on the horizontal axis, and the prices are the price is on the vertical axis. And again, this is not a smooth curve. However, it does have the shape of a demand function that is supposed to have, which is downward sloping. So this is downward sloping. So it's not smooth. However, sometimes in real world, your demand function is actually a shape like this. So this is how we can get the input demand and the output supply functions from the sensitivity analysis report. And that's all I want to cover for the linear programming problem. And next lecture, after your reading week, we will start with risk and production. And I hope you enjoy your break, which is a little bit late this year.